Hi, everyone. Why do we call these even functions, these graphs that are symmetric about the y-axis? Why do we call these functions even? Well, the kinds of functions that lead to these kinds of graphs with that kind of symmetry, they might be of the form f of x equals x to the second, and what else? F of x equals x to the fourth, x to the sixth, and so on. For that matter, x to the 0, which is basically what? This is basically 1, which is a constant function. Turns out there's a hole over here. We'll talk about him. And even something like x to the negative 2 and x to the negative 4. We'll talk about those. But it turns out that all these function rules, assuming that we're dealing with the implied domain, which would be all reals for these guys here, these are all going to be function rules for even functions with graphs that are symmetric about the y-axis. Let's talk more about these guys over here. F of x equals x to a positive even exponent. Their graphs will look like bowls, like these. Y equals x to the fourth, sixth, eighth, and so on. Their graphs will look like bowls. Let's go to Desmos. All right, so let's graph y equals x to the second. That's called a parabola, by the way. And then y equals x to the fourth. Now, technically, this is not a parabola. Only quadratics graph as parabolas. But still, y equals x to the fourth in blue here is still a bowl shape. And notice it does not fall below the x-axis because x to the fourth is never negative for real values of x, just like for squares. So we have two bowls here. Notice they're both symmetric about the y-axis. And not surprisingly, the blue parabola, y equals x to the fourth, out here is climbing more steeply than the red parabola, y equals x squared. So it's not surprising, for example, that, by the way, we're considering f of x equals x to the n, where n is an even positive integer for now, right? Although this is going to be even where n is any even integer. F would be an even function, all right? But going to these guys here, so if we have x to the second and x to the fourth, all right? Well, it's not surprising that if you take x values like 2, 3, and 4, it's not surprising at all that the fourth powers of those values will be greater than the second powers of those values. That's not a surprise. The fourth power of 3 is a lot more than the second power of 3. Okay, so it's not a surprise. It's not a surprise that the y-coordinates on the blue graph are higher than the y-coordinates on the red graph. But if we zoom in, we may be getting more of a surprise once we zoom in. Take a look what happens. Look at this. This might surprise you. If we zoom in close enough, close to x equals 0, specifically between -1 and +1, notice that the blue graph actually lags below the red graph. And that might surprise you, because you look out here and go, oh, the blue graph's above the red graph. Well, if you zoom in, you'll find that the blue graph does dip below the red graph over here. And in fact, in calculus, you're going to be asked to find the what? The area between the red graph and the blue graph. If you didn't know about the lag here, you might be going, what are you talking about? We're talking about these leaves here, the area of these leaves. Notice we have symmetry. And by the way, how many intersection points are there? See, this is where graphing utilities might fail you. If your window looks like this, you might go, oh, it looks like there's one intersection point at the origin. There are 3 intersection points. When does the fourth power of x equal the second power of x? Well, it's true that the square of 0 is 0 and the fourth power of 0 is 0. But that property is also true for +1. The fourth power is equal to the square. And it's also true for -1. The fourth power is equal to the square. Okay, so actually the blue and red graphs meet in 3 intersection points. And at these points, that's where the blue graph starts to lag beneath the red graph as you look inside. And they meet again at the origin. So why is that? All right. Well, for example, let's take a look at x equals 1/2, a number that's strictly between 0 and 1. The square of 1/2 is 1/2 times 1/2. That's 1/4. But the 4th power of 1/2 is, imagine a discount store that cuts prices in half every week. So cut in half, then cut another half, then cut another half, then cut another half. Those prices get very cheap. You're down to 1/16 of the original price. So if you start sticking in numbers strictly between 0 and 1, the 4th power is beaten by the 2nd power. The 4th power, okay, is less than the 2nd power. I'm sorry, I have it goes this way. The 4th power is less than the 2nd power. I wanted to say that the square of 1/2 is actually greater than the 4th power of 1/2, which might surprise you. The square beats the 4th power. The square beats the 4th power for these kinds of values of x. And at x equals 0 and x equals 1, and at x equals -1, there's a tie corresponding to these intersection points. But for values like 1/2 or 0.5, the red graph actually beats the blue graph in y coordinate. Here's 1/4, here's 1/16. I'll 1/2 comma 1/4 is on the red graph, square. I'll go back up here. 1/2 comma 1/16 over there in black. The red graph beats the blue graph for values like 1/2 or -1/2. That might surprise you. Hopefully not too much. All right. So in general, going back here, the x to the 4th graph is steeper out here compared to the red graph, but it's flatter near the origin. What about y equals x to the 6th? How's that compared to both these guys? Y equals x to the 6th. In green, it's steeper out here for values of x far from 0, but for values of x strictly between 0 and 1, maybe excluding 0, right? The green graph is below both the red graph and the blue graph. So again, the y equals x to the 6th graph in green, it's steeper out here, far away from x equals 0, but it's flatter over here, close to the origin. And again, you can talk about areas between various graphs. In calculus, you do that using definite integrals. All right, all of them are even. All of them represent even functions. Next up, how do we deal with y equals x to the 3rd, 5th, 7th, even 1st? Next time.